So next we're going to look at a question about isentropic efficiency. So we're going to look at question 8.11. Air is compressed by an adiabatic compressor from 27 degrees Celsius and 95 kilopascals to 277 degrees Celsius and 600 kilopascals. Determine the isentropic efficiency of the compressor and the exit temperature of air for the isentropic case. Assume constant air properties evaluated at room temperature. So we have a compressor. Compressors always require us to put in work. And ideally, yes, a compressor is isentropic, which means adiabatic and reversible. But practically speaking, it's more closely resembling just an adiabatic process, meaning there are, friction and other effects that make it so it's not perfectly isentropic. So the question is, well, how close do we come to being perfectly isentropic? Because it can be maybe just a little bit off, or we can be way off and be producing a lot of entropy. So the question is to find that isentropic efficiency. So the equation that we're going to use for isentropic efficiency of a compressor is going to be the amount of work that's actually required compared to the ideal case, which is the isentropic case, right? So the more work beyond the isentropic case that's required means the less isentropically efficient the system is. And that's bad. We want as close as we can to simulate an isentropic process, which means we want as high an isentropic efficiency as possible. Remember, putting in work to the compressor means that's less net work you get from the system. That's not good. So let's see how to calculate this. So we're going from state 1 to state 2. What we'll do is we're going to make use of, again, the isentropic relations that we saw, because all we know at the moment is that we're changing from one temperature to another, but we don't really know what the ideal case would be. So we're going to use the isentropic relationships. Even though this isn't an isentropic process, we're going to use those to see and to simulate what it would be like if we were being isentropic, and that way we have what to compare things to. All right. So if we remember the isentropic relationship, we can say T2 over T1 equals P2 over P1 to the power of gamma minus 1 over gamma, where for air, and this is the case in this question, gamma is 1.4. Now T1 and P1 are, what we start at. That doesn't change. But of course, T2 and P2, we're going to put a little s to denote that this isn't really what the pressure and temperature are by the end of the process, but this is what it would be if we had it our way and if this was a perfectly isentropic process. So let me just get the numbers again, because I don't remember what they are. Okay, my mistake there. Anyways, we're doing this to find what the temperature would be at the end of an isentropic process, so we can isolate for temperature. T2s equals T1 times P2s over P1 to the gamma minus 1 over gamma. So T1 was known as 27 degrees Celsius, but again, we always have to convert that in these types of cases to Kelvin. So plus 273 gives us 300 Kelvin. Now, P2s is just P2, because when you talk about a compressor, you design the compressor to work to bring something from pressure 1 to pressure 2. Whether it does it isentropically or not, it doesn't care, but it will bring it to that pressure. So P2s really is P2. So we're going from, 600 is where we end up, and we're starting at 95. And gamma minus 1 over gamma, so 0.4 over 1.4. And if we calculate this, we'll get T2s of 508 Kelvin. So that means in a perfect world, in order to go from 95 kilopascals to 600, from 95 kilopascals to 600 kilopascals, the temperature would have to increase to 508. But this isn't a perfect world. We have some isentropic inefficiency, which is going to make it so that we have to even go to a higher temperature than the bare minimum. And that means we have to put in more work. And we don't want to put in more work than we have to. So let's see how much more work we need to put in. So if you remember, a compressor, the isentropic efficiency of a compressor is the amount of work, the amount of work, I said something wrong earlier. It's the amount of work that we would ideally do over the amount of work that we actually end up doing. So that's the opposite of what I said initially. So that was wrong, the first thing I said. So just to reiterate, the isentropic efficiency is the work that we would ideally isentropically do versus the work that we actually have to do. So of course, work for an ideal gas, Cp delta T. In the first case, for the ideal case, delta T is just T2 isentropic minus T1 over Cp times the real case, which is T2 minus T1, and they tell us T2 and T1. Let me just check what T2 was, because I don't remember. T2 was 277 degrees Celsius. So going to Kelvin, that's 550. 550 minus T1, which was 300. And this here is 508, which is what we calculated. So again, you see that the actual temperature is higher than what it would theoretically be in the perfectly isentropic case, and that's bad. That means we had to put in more work. So if we cross out these, we get 508 minus 300 over 550 minus 300, and this will give us a value of 0.832. So we are 0.832 or 83.2% of the way to being isentropic.